Thank you, Mr. Sedmak, for the kind introduction. I want to welcome you all to my presentation titled Great Propagation in Additive Manufactured Materials and Structures. This study was performed at the University of Paderborn and in a close collaboration with the Direct Manufacturing Research Center. And the Institute of the Applied Mechanics was headed in this time by Professor Richard. And since a few months I changed to the class company, and we are dealing with tractors and combines. Now let's start with the agenda for today. I will show you for first the basic steps of the laser melting process that was used in order to manufacture parts and samples that were investigated in this work. Then I give you some results considering crack growth and the influencing factors on the crack growth performance. And the next part deals with the numerical investigation of crack growth and the effect of heat treatment was investigated on the residual lifetime of an implant. So, and the last part are the major conclusions of this work. Now, the part fabrication by laser melting is divided in three basic steps. The first one is the recoding step. The second one is the irradiation step, and the last one is the platform lowering. Due to this layer-wise manufacturing, it's possible to produce complex parts and individualized parts. And here on the right, you can see final product and a hip joint implant. So, the first step. You have the recorder unit, which is moving over the building chamber, and here powderized material is put on the surface, which is molten in the next step by the laser beam and solidifies this part here in the powder. And the last step is lowering of the building platform down, so we get here the space for the new recording step. The materials that I analyzed were the titanium alloy T64 and the stainless steel, the austenitic stainless steel. Here we can see the spheric shape of the powder, which were used for manufacturing, and the deviation of the particle size. So we had an average particle size of about 40 microns. The next point, which should have an influence on the crack growth data, is the building direction. Here we considered two different building directions. That means building direction is normal to the crack growth direction, and the building direction here is parallel to the crack growth direction. Another point that was investigated is the heat treatment. Three different heat treatments we analyzed. The first one is only the stress relieving treatment, where we get out that we are able to remove the residual stresses out of the part. The next point is the so-called hot isostatic repressing. Here the parts are applied to a high pressure and a high temperature, and after this treatment, you can see here at the bottom in the image, it's a CT scan, we are able to minimize the defects, the pores, or even to remove them from the part. The last heat treatment was the treatment at higher temperatures. Here modifications in the microstructure are able, and we change the microstructure from the montensity structure in the built condition to a coarse grain microstructure after this treatment. The last point that was investigated in this work is the build-up rate. Here we analyzed it on the stainless steel, and we the build-up rate was varied between 10 and 16 cubic centimeters per hour, and this is necessary in order to get a high efficiency for production parts. So let's have a look on the results. Here we have crack growth curves. I analyzed, we have here 3 different crack growth curves colored in one color. So you can see the build condition, and on the right side we have the reference material that was tested in our laboratory at the same conditions, and we can see that the data for the build condition is not as good as for the reference material. This could be improved, but by the treatment at higher temperatures, while the scattering is high here. And if we have a look on the 800-degree treatment, so we have here 3 different crack growth curves, which show no scattering and are at the threshold values of the reference material. And we are able even to increase this performance by hot isostatically pressing. Now here in the table we have the values. So we have increase from 1.4 from the build condition to a value of 4 for the heat condition. And so we are able to match the reference material. On this slide I want to show you the crack growth data for both building directions and the tensile stress and the yield stress in one diagram, which was normalized, and we have at the outer line the best possible performance, and what we can see here, we have this balance between the quasi-static values and the fraction mechanical values. This can be improved by heat treatment at 800-degree condition, and for the 1050 and hot isostatic repressing, we get a well-balanced crack growth data. So let's have a look on the build-up rates. Here we have an increase from blue to 10 to black in the build-up rate. That means from 10 to 16 cubic centimeters per hour, and we can see that there is a decrease in the threshold values. In the Paris region and at the higher stress intensity ranges, we have a similar performance. And if we have a look on this diagram again, here I have the elongation and break, the yield strength, tensile stress, tensile strength, and the both fracture mechanical values and the build-up rate. So let's turn to the higher build-up rate, and the higher build-up rates leads to a decrease in elongation at break and in the threshold value of about 40%. So this data was used in order to have a look how the heat treatment affect the residual lifetime of an implant, and for this the loading case normal walking was selected, and the R ratio was 0.5, and the material was used the T64 material, and the data I presented you before was fitted um, the curves were fitted to the data I presented before due to the Forman-Menu equation, and here are the parameters that I used for the numerical simulation, and the crack was assumed at the region of highest maximum principal stresses, and the meshing, and we have a fine mesh here in the region of the crack tip. So the results show that we are able to increase the lifetime of about factor of about 25, and it's only by removing the residual stresses from the material. So let me summarize the major conclusions. The heat treatment has significantly effect on the fraction mechanical data, and the HIP was here with the best balance of mechanical and fraction mechanical properties. The increase in the build-up rate show that we have a decrease in the threshold value. That means a decrease in the crack growth performance. And at the end, we found out that the lifetime can be significantly improved only by removing the residual stresses.